optional readings. Okay. So for today's lecture, we are going to go through this following three material. So first, we usually begin the class meeting with the lecture itself. And then for today's topic, as I mentioned, we'll be focusing on the ordinary least square model, the OLS model, for the first couple of weeks, which is also our workforce model in this course. So for today's lectures, because we're going to spend more than 2 hours talking about that, so it's quite tedious, but it's necessary. So I consider that as a necessary evil. For the rest of this semester, we wouldn't be needed that much time, but for today, just bear with me. Right? So we want to make sure that you have this following material. So first, we got a lecture note, which we can you can get it from our shared Dropbox folder or also from the TU course, the online course below. Just in case you didn't receive my email, because some of you forget to check your TU mail regularly, just as I do, because I rarely use my TU mail. And so I also put it in Dropbox folder and also send you to the course folder in case you didn't receive my email. So we're going to quickly go through it in our discussion of the OLS model. But you don't need to get too fixated on the mathematical details. I just want to use that to show that what's really going on behind under the hood of this R console. Doing this in R is relatively easy. Just want to make sure that you can also get access to our R-Parts page. Are we on the same page? If you couldn't find it, just go to Google. Even though I kind of hate to say that, and be responsible, say, hey, Google it. But if you couldn't find it, just go to Google, type R-Parts, HKPSCNG, abbreviation, and then you'll find it. Okay? Any questions before we start? Easy. Cool. All right, so again, lecture is OLS model, like the model of statistical model. We can spend quite some time talking about correlation. Then jump to linear regression model, aka OLS model. So the method is it's probably hard for you to imagine at the moment. It's freezing in code, right? So just in a couple of months, you're gonna need ice cream. Or something code. Okay. Probably in 3 months from now, you're gonna need say one quench your thirst, or just you're tiresome with probably the cold beer, just not encouraging to drink alcohol, and or just some kind of ice cream. Okay. So you might notice that. So suppose you secure a job at a consulting firm as a business analyst, could be a business intelligence analyst. And then your company, your employer sent you to investigate the correlation between temperature and ice cream sale. And you find out that, okay, every summer, getting probably late May or mid-May, you find out that ice cream sales go up. So what's going on here? Seems like there's some binary correlation between these two phenomena. First, temperature goes up, and then ice cream sales goes up. But on the other hand, you also notice that, okay, so it seems that the average lengths are shorter and shorter over time. Right? All these phenomena somehow correlated. could say, okay, so I surmise, I guess, ice cream sale volume, number of ice cream sale per year is correlated with the temperature. So whenever temperature goes up, then you might expect ice cream sale to also go up. Or the other way around, is because, okay, ice cream sale go up, so does the temperature. Does that make any sense? We actually don't. Or maybe it's a survey. If the survey becomes shorter, then it's inversely correlated with temperature. Or maybe it's the other way around, because temperature goes up and then surge length becomes shorter, or we reduce the average length of average surge length. Or on the other hand, you might also expect, okay, so maybe there's some correlation between ice cream sales. So what is correlation? I mean, in statistical column, correlation is any sort of relationship between binary data, means that when I say bi, means that it's a two variable, or between any random variable. Right? And the most common usage, when we're talking about statistical correlation, we're talking about the linear relationship between a pair of variables, could be, for example, x and y. But of course, that doesn't imply causation. You can actually use y as the x here and put x on the left-hand side of it. So the first thing to know in statistics, even if some of you might have, that's not the first thing, is it doesn't necessarily imply causation. But try to think about cancer and smoking, right? They have kind of a well-studied subject. So when I tried to talk to a friend of mine who studied medicine, said it's causally related. He said, I have no idea what you're talking about, because there are a bunch of substances in the cigarette, in the pack of cigarette. And nearly all of them can cause cancer. But cancer can be triggered by lots of genes, or some sort of like genetic issues, or maybe some condition that's inherent in your body. So there are multiple causal paths, and I'm not sure which one you are referring to. So that means, okay, so maybe causation does exist, but we actually have a hard time identifying which variable led to which outcome, or maybe it's the other way around. So whenever you're doing statistical analysis, you must be very careful in making your claim. So how does this done statistically? How can we somehow probe this relationship and prove that with some, say, hard evidence or statistical evidence that this relationship does exist? And also, suppose that we have done this in some sort of statistical model. So what can we infer? What kind of data or what kind of statistic, numbers, variables, or graphical or visualization evidence that we should look at? So just going back to our previous example. So we know that, okay, so maybe search then is somehow determined by temperature and ice cream sale. So we just suppose that, okay, so this is our outcome variable, suppose that that's our y, the dependent variable. And then it's driven by temperature, and it's a function of the temperature of ice cream sale. Right? That makes sense. Or actually doesn't. Okay. So a related concept is called model specification. So whenever you're trying to, for example, if you're trying to buy or purchase a computer from a website, say the Lenovo or Apple website, and you might click on the specification because the vendor will ask you, so what spec, what product spec you're looking for. I say I want an Intel i7, right? And then want lots of memory. Or maybe you're just living in a extremely poor condition and say, oh no, I don't need that. I just want a bare minimum, right? So different people look for different certification. This is the same with model with statistical estimation. Because specification tells us, or maybe it's the other way. We tell your programming language, your statistical package, that what we want to see in the model, in that what variable should be included in the model as an estimator for the outcome variable of interest. Also, what variable, and also what variable should be put on the left-hand side of the model as our outcome variable, as well as how they should be measured. Should we measure that in centimeter or in inches? Kilometer, we don't know. Right, so there are lots of model specification. We can also say, well, because as we said just a couple of minutes ago, everything's related, and we actually have a hard time identifying which variable caused which variable to occur. So we can presumably also put ice cream cell on the left-hand side as our dependent variable, and two other variables on the right-hand side as our explanatory variable, or some sort of independent variable, the IV, right? And here is the DV. Or maybe this way, right? We can also do it this way. Or maybe there's some variable we have omitted. Maybe the number of tree that causes temperature to rise, right? Think about the greenhouse emission and environmental protection, that kind of thing. So if you want to conceptualize all this into a statistical model, then you simply do this. It's pretty much like ingrained to all kinds of statistical package. You simply simply tell your computer that, okay, so this will be my dependent variable, and I want to exploit that variable on the right-hand side of the equation, and then regress dependent variable on the list of independent variable to get the coefficient. Coefficient is actually a measure of the effect, or it's simply the degree of correlation between this independent exponent variable and the dependent variable of interest. So the beta term is called coefficient. It's a measure of the degree of correlation between these two variables. Or if you study social science, right? Well, actually, I think that social science would love to use this term. I'm going to call it the coefficient as effect. In that 1 unit increase in this variable can increase or decrease depending on the sign in the positive negative of the coefficient. Decrease ice cream cell by this amount of effect, by beta 1 amount of effect. You can say if you measure the ice cream cell by pint, you can say, okay, so 1 degree Celsius or 1 degree Fahrenheit increase in temperature will lead to maybe a 1,000 high or 1 ton increase in ice cream cell, in monthly ice cream cell. So that would be the effect of temperature on ice cream. So the measurement unit does matter. So if you want to present this result to your supervisor, you want to say that, okay, so under my supervision, because I'm like a strategy advisor to the ice cream company. So their monthly ice cream sale increased by, say, 10,000 pi. Well, so your supervisor might really impressed with your performance. But if you measure that in ton, that's probably just less than 1 ton, or maybe like just a couple tons. Oh, that's okay. Just a meager increase. And you at the end of the day, you might be fired. I'm not sure. The same as the beta 2, right? So you can keep adding those variables at the right hand side of it. But you might also notice that there's an epsilon. So what's that? This is called the error term, which is just a collection of unknown, unspecified parameters. When I say unspecified, I mean that, okay, so here's my specification of statistical model. mean that which variable, because there's a variable that I want to put on the right-hand side of the equations. So for those variables that have not been included in the statistical model, they are the unspecified parameter. Okay, that makes sense? Okay. But whenever you try to use the regression model to explain things or to make prediction on the outcome variable, they always generate some sort of error, modeling error, because you cannot perfectly predict how many ice cream sell in that season or within a particular week, and there always some certain amount of error. And the error could be just maybe the variable isn't that good, maybe not a good predictor for the outcome variable intro, or maybe some measurement error, or there may be some unspecified variable that are actually influencing the outcome. For example, number of trees, can you forget to put into this two-period model specification? And it turned out that it may turn out that it's actually a very important variable. We don't know. So those are unspecified variables, and they are the origin of this error. And our task, of course, is to reduce the amount of error. The model with the smallest error is the best model. And we already go through this, right? Then we come to how to interpret this coefficient thing. Okay, so you might expect that, okay, just from an intuitive sense that, okay, so ice cream cell should be more related to temperature instead of skirt length, because that doesn't make any practical sense. So I might expect that, okay, the coefficient of temperature should be larger than the coefficient of skirt length, right? And talk about significance. We're actually going to talk about it later in just an hour. You might also expect that, okay, given that temperature is a more important factor for explaining ice cream cells, so it might be more significant. And on the other hand, or on the contrary, skirt length might turn out to be insignificant. It cannot be used as a predictor for the outcome variable in ice cream cells. And we might also expect that, okay, the three variables are correlated with each other to some degree. Everything is correlated to some degree. Or it may be some variable in the context, for example, the number of trees, but we just fail to incorporate that into a model specification. That might be driving the outcome variable in track. But it's only just that we actually do not have a very good a priori knowledge as to what those unspecified variables are. And in statistical politics, we call this omitted variable bias, because those variables are omitted. And it turned out that they cannot bias in our estimation. So actually, I would say the scientific community actually derive lots of publications on it. For example, someone published an article saying that temperature is an important factor for exploding ice cream cell. And then you say, no, not true, because my model suggests that number of trees is more important. And then you close then the publication. That is the device-wise scientific research. And more importantly, another important area of research in linear regression model, as well as all statistical models. It pays also attention to the error term, because in linear regression model, we assume that the error term a good model is one that has the smallest error term. So we assume that, okay, even though that exists, they should assume to be normally distributed with some pretty fine range of the error term, which should be plotted. Meaning that all the diagonal, we'll actually get to this real quick, are 0. So that, okay, so given all this result, suppose we have run a regression and turned out that, okay, so temperature does increase ice cream cell, and it's very significant. So what can we learn from this model and make say it can recommend some actionable strategy to the ice cream company. So for example, you might write at the very end of the research paper saying that, okay, so our consulting company were advised that so your sale were increased whenever temperature goes up, right? So in the future, if the temperature were to go up, then ice cream vendors should expect their sales volume to increase, right? But on the other hand, if you run a very rigorous statistical model, it turns out that, okay, so there's actually the spirit phase is actually driving this relationship and the increased ice cream sale. Then perhaps all this set of the interrelationship between the three variables maybe worse follow or maybe you there's some coding error in your programming code. Not sure. Or maybe there's an unspecified variable in error term. They are the culprit, right? The bias in this estimation. Right. So what other very obvious negative or positive association are we likely to encounter in our daily life? It's not a very scientific question. I'll just supply an example. Right, so I guess I will provide one. Anyone watch basketball? No? Okay. Ever heard of this guy? Jabbar is the NBA leading scorer. Right. So I mean, he's also very intrigued by the current trend of three-point shot because he's that. Oh, this young generation player are so fascinated, infatuated with three-point. So to the point that almost stopped practicing like quick shoot. That's why he cut his teeth. Right? And how do you find out this association? I would like him to speak for himself.
They don't seem to understand that. That was the first thing that I learned, and they don't get to realize that if you get close to the basket, a lot more of your shots will go in.
Right. So apparently there's a negative association between this negative association between the distance or between the distance where you stand to the rim and the probability that your shot will go in. Right, so there's negative association, pretty obvious. Actually, there's a there's a bunch of sports analysts actually try to analyze which position will make the best shot in the pen area. So if you want to do a term paper on this, I would encourage you to do that. Okay, so continue. Right, so finally we get to the linear regression model. So if you read those texts, you'll find out that, okay, so they usually write a linear equation this way. So first we have dependent variable interest, right? And we also have a subscript, meaning that, okay, that's the ith observation. First, you have the first observation, second observation, third observations, all the way up to the nth observation. And n is your total number of observations for a given data set. Right? Then we also have a constant term, that's what we call constant, meaning that no matter what you put into the model, and for example, ice cream sale is going to increase by this given amount, no matter what you put into the regression model. And the x1 is the explanatory variable of interest. It's what you want to explain the outcome variable with. And then our friend, the error term. So now we refer back to the specification. Specification is the process, but it's more of an art for determining which variable that I should put into the model and which one to be excluded. So you might say, if I keep adding those variables into the model, wasn't that good? Because eventually I'm going to find out this important variable that helps explain all the relationships, or at least 99.9% of the relationship. Outcome variable. Well, it's not necessarily always so good because, as we will find out next week, you kind of keep inflating the correlation between this redundant variable and other variable. So eventually your model might explode. So it's actually or simply summarize this term. So less is more. If you can find, if you're able to explain, say, a major proportion of the variance in the outcome variable was just only a few independent variable, explanatory variable, then I would say you have a really good model instead of just writing a long equation that also explanatory variable. So less is more. Meaning that you have to make a wise decision in terms of what to include, what to exclude from the regression equation. Another important thing about the functional form is the way by which an independent explanatory variable or independent variable is related to the dependent variable of interest. That should be determined by, or I guess the best way to determine what this relationship should look like is simply to plot it out. For example, you might find out, okay, so we always assume that okay, y is a function of x, right? But it turns out that okay, so maybe the two variables share some sort of quadratic relationship, meaning that as x increase, and then you kind of experience a sudden jump in its relationship with y. So we can use square term to capture this quadratic relationship. Or you might find out that okay, the relationship between x and y is somehow moderated by another variable who, for example, like say, where you see British research. And more importantly, z has a nonlinear relationship with y. So this inherently by or second lift. I want to delve deeper into this question to look at what exactly are their interrelationships. We're going to find out in a week or 4 weeks. So it defined the relationship between, through the specification process, defined the relationship between the independent variable and the dependent variable. Right? And what's the science behind the linear regression model, they call the linear algebra. Anyone taken a course in linear algebra before? Cool. All right, so for example, so suppose we were given a set of data with an observation, right? So in statistics, we'll say data science. But an observation means that so suppose you open out an Excel or CSV spreadsheet, right? The first thing to know is that okay, it's usually organized into for example, row and column format. Okay. So we usually have, for example, an observation. and each observation is a row. Right? They say, so what's the other dimension? Well, the other dimension is the column. Column means that the total number of variables we have, or in engineering, called a feature. Right. So suppose you try to measure the what attribute or what specific aspect of the product that people buy. So there are different features associated with the product. For example, the price, how it looks, shape, weight, right, or color. So those constitute one dimension in the data. So that's usually we denote it under a column. So column 1, column 2. So if you try to delineate the contour of a human being, you say it could be his or her height, her weight, and gender. Right? So that's the total number of variables. And we actually call it a design matrix. So entry of value defined by a set of objects. So in linear algebra, we simply enter that in matrix. Right? So the first is an n by 1 column. So we have this our outcome variable of interest, and we have our constant term. Note that they are all the same across all an observation. Right? We also have our variable and this coefficient plus the also n by 1, the error column. Right? So I think that this would be easier to understand. Right? So if we decompose this part by the design matrix, which is denoted by 1 plus the explanatory variable of interest, and their associated coefficient. So we can actually generate this part through matrix multiplication. Simply multiply the first row by their associated coefficients plus the error term. So whenever we speak about the matrix in linear algebra, first thing to know is dimension. So we say the dimension of the matrix are the number of rows, right? We have for the n row, but just only one column, right? So we should know that, okay, so it's the number of row by, or simply you could say times the number of column. So we say, so this part, the design matrix is n by 2 matrix. Means that 2 row, there's n row, 2 column. So it works the same way. For example, in R programming, you need to type. So given that you're given a matrix object of n, say, okay, I want to find out the entry in R's sorry, in the R's row and 6th column. You simply type, for example, the first row, 2nd column, you type n in the square bracket. The first row, 2nd column, then R will return you with the entry, or saying the value of the entry in this particular location. And this part, we usually call this part as design matrix, as I just said before. It's a matrix of value, because they contain real value. For example, you can say they contain this linear combination of value corresponding to various attributes of a person, for example, height, weight, or gender. So the matrix of values will explain the variable. Actually, some statisticians like to call it as a regressor, represented by a set of objects. While the beta is or as you know it, is a vector of coefficient indicating the degree of association between the explanatory variable and the outcome variable of interest. While the beta 0 is what we usually call constant. It's a common intercept for all observations, so the value is the same across all an observation. Or the error term is of particular importance. Okay, its dimension is n times n by 1, but its distribution is assumed to be independent, meaning that okay, the first observation's error term is unrelated to the second observation's error term. And also, the second observation error term is unrelated to the error term in the first one, as well as the last observation. They're independent, means that they're uncorrelated with each other. And even if they were to exist, of course, because you rarely get an error term of just exactly zero. So there's definitely some disturbance in terms of distribution error term. But even if they were to exist, they are identically distributed. And their distribution follow a normal distribution with mean, should probably erase this. With mean 0 and some estimable variance. We usually denote that as, well, with normal distribution with mean 0, the first this abbreviation means normal distribution, distributed normally with mean 0 and some estimable variance. These probably just stand out. And if I wanted to know the distribution of a particular variable, say maybe some x or simply some equation, to say they follow IID distribution. Simply put it about a delta sign. That means they follow independent and identical distribution, so IID distribution. As I said here. So you might notice that okay, in some statistical, some textbook, combination textbook, so that people would like to put an I here. I is actually the identity matrix. We're going to get to this real quick. Meaning that, well, if the error term distributions, if they were to follow an IID distribution, and suppose we're living in a perfect world, right? So all these one variable are uncorrelated with each other. They uncorrelated with each other. So their covariance are 0. So what's being left is just their variance with itself. So that we only have this one in that n by n identity matrix. So the only variance, which is very estimable, are those on the we're going to talk about on those on the main diagonal, which should be exactly 1, because simply your correlation with yourself. For all other off-diagonal elements, colored in blue, they're 0. But I mean, those are very big assumptions to make, given that we live in a perfect world, because usually we don't. Right, so we're going to get back to previous example. That implies that, okay, the error term has a uniform variance across all the observation. And there's no serial dependence between observations. For example, the first observation's error term is not correlated with the error term of the second observation. The second observation's error term is not correlated with the first observation and the last observation, etc. And this we usually call this condition uniform distribution as homoscedasticity, meaning that the possible distribution, we like to make an assumption about the distribution error. distribution of the error term for the first observation. Suppose that is our just trying to think of it as a 3D surface or first observation. Here's some sort of error term. We follow a normal distribution with mean 0 and some estimable variance. And then for the second observation, you also have the same form of error term distribution. And so on for the third observation, fourth observation, fifth observation, and last observation. They don't have the same form of error term distribution. We call it homoscedasticity. In multivariate regression, because here I assume that there's a 3D, we have to lie on a 3D surface. But of course, as you keep adding one additional variable into the regression equation, then we kind of expand the dimension of the surface. So eventually you will become like a bowl-shaped object. Right? So it's also called spherical error. Usually assuming that all the explanatory variable, x1 up to xk, are all follow multivariate normal distribution with the set I equal. So you were assuming that you have the mean for all observation lying at the center of this bowl-shaped object with a radius of sigma, which is your standard error, spanned by the total k number of x. Here we have k variable, meaning that you use x to expand this object into a k-dimensional space. Exactly, you eventually become like a bowl-shaped object. So it's called a spherical error. Here, one dimension is one sphere. So you say, okay, so judging from my really rudimentary English, I know that homo means that the same, right? So it means that there must be something that called haploid. Something is not the same. So of course, they do exist. They call it heteroscedasticity. So that occurs when the error is, so for example, when some multiple error are correlated. So suppose for some reason, it's supposed to be first observations, but we're gathering data to study the student cohort, study cohort effect on students. But it turned out that the first observation and the second observation they're classmates with the same major. So there's definitely some correlation, right? And so they happen to take the same class together. And then you distribute survey asking how will you rate this class? And it turned out that okay, because they'll skip that class, so they hate that class a lot. So you find out that the error term are quite correlated. And the condition of homoscedasticity assumption is violated when at least one the error term not normally distributed. It could be correlated with the error term, or maybe just measurement error code, or maybe two, or at least more than one of the explanatory variable. Here I only put one here. Are correlated. You can say, for example, in some cohort study, people want to study the effect of age on, say, people's decision to have one additional child. But it seems that since you probably, everyone you have certain age, your propensity to have another child probably decrease, right? So people want to study this cohort effect. Say, okay, so maybe on my first variable for some age. In my second variable, I assume that it follows the quadratic relationship, h squared. So they are somehow correlated, right? So that means this condition is slightly offended, slightly violated. So now we get back to our dependent variable interest. So you might ask, well, why will this matter? It's very natural that different people have different value in those variables that are incorporated in the design matrix. Well, that does matter in terms of estimation because we are going to get average. We are going to get average response on all these people and then use that as a predicted value for the y variable, the outcome variable of interest. Because it's a vector outcome variable that we want to estimate with all the values that we include as a explanatory variable. Right? But however, the outcome variable actually differ across all the observations. You can say like human height, people differ dramatically in terms of their height, weight, right? And also, I want to make sure that the y, forms of y also determine what kind of statistical model you want to use. Because y can take different forms. For example, in Euler-Ritz model, we simply measure a continuous variable, so that the explanatory variable and outcome variable has linear relationship. One unit increase in the explanatory variable lead to beta 1 increase or decrease in the dependent variable. But okay, so there are also different types of dependent variable that we're looking at. For example, so if you have many categories that can be ranked in ordinal scale, say you have 10 categories, I like it very much, not so much, I like it, I'm neutral on that. Then you could plausibly use OLS for this purposes. But if you're forced to answer the question, for example, I ask you to, for example, today's hottest topic. Just I point a gun in your head and ask you to choose side between Russia and Ukraine, right? Which side do you support? Then you must answer at least one. Right? So it could be also distributed on a binary scale. Whether people would test positive, in fact it was COVID, or negative. And in that case, you cannot use ordinary least square model. Or we may be dealing with categorical data, so there is no inherent ranking, inherent order. For example, which ice cream flavor do you like? So you cannot probably say chocolate is better than strawberry, because from your perspective, some people might not like strawberry over chocolate. Or party identification, right? Republican, Democrat, KMT or DPP, right? You cannot say which one is better than which one. It's your personality, right? And that's because each observation has a unique explanatory variable, a unique value on a particular explanatory variable. So that the B, their beta coefficient, may also vary across observation, right? And since we assume that the outcome variable of interest is a linear combination of the explanatory variable that you put on the right-hand side of the equation, so that its values, predicted value, also vary in terms of different combination of the explanatory variable that you put on the right-hand side of the equation across all the observation. Any question here? All right, so let's get to the average. So suppose, let me finish this. So suppose you're given two explanatory variable x1 and x2. So you can generate a 2x2 covariance matrix. Right? So if you were given 3 variables, then you should be able to generate 3x3 variance covariance matrix. So the first one on the upper left of this variance covariance matrix is the variance of the first variable, which is just its correlation with itself. So you should know intuitively that it should be 1, right? And same with the variances on the lower right.